Hi, and welcome to Module 8 of Lecture 1. This module is the first in Part 2 of Lecture 1, which moves on from talking about theory and science to talking about measurement and research design. Research design is simply the set of procedures that we use to draw valid inferences in order to test our hypotheses. The first question we ask in research design is, what data are relevant? What data do we need to acquire and use to actually test our hypotheses? To answer that question, we need to ask the question of what comparisons do we need to make to test our hypotheses. A good design will ensure that the data that we examine will allow us to draw the inferences and answer our research question, which we can do by testing our hypotheses. The purpose of research design, again, is to ensure that the inferences we draw are valid. To achieve that goal, good designs will A, account for threats to valid inference, the kind of threats we talked about in the previous module. B, identify an appropriate unit of observation. And this is non-trivial. We need to know what the unit of observation is. Do we care about the country level or the state level or the local level or the individual level? These are all questions we need to answer in a good design. And 3, identify an appropriate level, temporal or spatial domain. So where's the variation happening? Across time, across space, both? These are all questions that a good design will answer. The cornerstone of good design is comparison. We're trying to compare, for instance, values of some dependent variable y across space, so across individuals or states or countries at a given time. Or we're trying to compare values of some dependent variable y across time, across decades or years or months, or both at the same time. The design will identify what kind of comparisons we are making. The key to these comparisons, and this is the key to all design, is that causal processes must be the same across units. So we must compare 2 or more units to assess if we can infer that X causes Y. So for instance, does rainfall influence turnout? The answer is yes, we think. For that, we're asking a question of comparison. Is the turnout greater in a precinct that received no rain compared to a precinct that received rain? The comparison here is central to our analysis, right? We're comparing the precinct with rain to the one without rain. We also must ask, though, the how-else question. Were those precincts different in other ways besides rainfall that might be important? And here you can hopefully see what we're getting at here. If we have 2 precincts, one of which has rainfall and one of which does not, we want to attribute the difference in turnout to rainfall. The problem is any other difference between those 2 units, between those 2 precincts, that we might also be true, might lead to a poor inference, might lead to threats to our inference due to spurious causation or anything else, right? There could be other differences between those 2 units that are responsible for the difference in turnout between the precincts that are not rainfall. In essence, we want to isolate the rainfall difference and have everything else be the same. That's key. So our goal is maximum comparability, right? We want these 2 units that we're comparing, these 2 precincts in that case, to be identical except for the independent variable of interest. The best sort of gold standard to do this is via random assignment. The goal would be to take a large population of individuals, the larger the better, assign them at random to the 2 precincts, and then assign the treatment of rainfall in this case at random. That's random assignment. That's sort of the gold standard. These randomized controlled trials, or RCTs, are the gold standard of experimental inference. And we'll get to that in a little more detail. And that's most of what we're doing in practice is not going to get to that gold standard. And a lot of what we'll talk about are ways to get as close as possible to that experimental gold standard. Other ways to maximize comparability are ways that involve sort of a reduction from that gold standard. A standard way we're going to talk about mostly in this course is statistical control. So we won't actually control for all the other things that could be different in practice, but we'll try to account for the differences that we observe between the 2 different units of analysis. Between the 2 different units in our setting. So in this case, between the 2 different precincts. We try to include all the differences we thought might matter between precinct 1 and precinct 2, besides rainfall differences and control for them statistically. And we'll learn how to do that in this course. Other ways involve things like matching. So the idea is to construct different cases that seem the same on all relevant dimensions that we think matter, except for rainfall. There are other ways to do that. Well, trying to figure out how best to do inference on observational data, on non-experimental data, is a vibrant area of research, and one very important because it's not always easy to, as we'll note in a second, to randomize. Okay, so let's look at some examples first. This is a comparison across time of traffic fatalities in Connecticut in the 50s. So we see it bounces around, obviously, because there's randomness involved in traffic fatalities. And then it spikes right around here, and then there's a treatment right around here, and then it drops precipitously and it goes down after that treatment a whole bunch. But notice it starts dropping potentially before or potentially after the treatment, we're not sure. And we see before the treatment 324 deaths, after the treatment 284, and it keeps going down afterward. So the question is, did the program that happened at this treatment actually cause a reduction in traffic deaths, or was it just something else? That's the key, and that's the key question we want to ask in this particular example's case, and that's the key to all the things we do. We have some policy, we have some action, and we're trying to see if that policy or action has an actual effect, or if the effect we observe is due to something else. That, as we said at the beginning of this course, that's important for any kind of policy analysis, any kind of policy making, is to understand how these policies work, and do they work at all. So let's start by defining here internal validity again. Here we defined internal validity before in the theoretical sense in terms of having our steps follow from each other logically. And the internal validity definition here on the empirical side is very similar. It's, does the change in the independent variable really cause the change we observe in the values of the dependent variable? Right? Does the x lead to the y? Theoretically, it was, does x lead to y logically? Empirically is, does x cause y in practice? There are lots of threats to internal validity. The empirical threats like history. There might be concurrent events happening at the same time as the treatment happened that could lead to changes, right? Maybe it wasn't that at the point of that treatment right here, maybe it wasn't that the treatment had a massive effect and dropped and plummeted and had fatalities plummet. Maybe it's just random effects and happened to be a bump right here. Oh, sorry, maybe there was another historical thing that happened around the same time period that led to the decrease. We don't know. Maybe just maturation, the passage of time itself led to the decrease after a while. Maybe people learned over time to drive less badly and have fewer accidents. Or maybe there was some other event, this is also like history, some other event, some change in traffic patterns, some change in work patterns that led to less driving. Maybe there's some event before the experiment in which people just started driving less. Right? As I said before, this video was recorded during COVID-19 stay-at-home orders, and the traffic patterns have changed massively. That would not be part of any kind of policy that someone instituted to try to reduce traffic fatalities. It would just be an event that happened before the experiment happened that led to continued effects. It could just be regression to the mean, and it seems like in this case it might be. So, for instance, any kind of probabilistic event, right, has some randomness associated with it, right? It's going down and up and down and up and down and up and so on, right? Well, maybe this big up right here was just random, and then after a while it went down again because the mean of traffic fatalities is somewhere around here, and so after the spike, it went back down to the mean. That happens all the time. I have free throw example written here because it happens all the time in sports, right? Someone will go on a hot streak. It doesn't necessarily mean that they're just better now. It might mean they have a string of luck, and after luck runs out, they go back to their mean behavior. So maybe it's not the treatment that matters, it's just reversion to the mean. Or maybe it's selection. Maybe we happen to choose cases that made this look like this, right? Maybe we chose our cases of fatalities for Connecticut that happened to have this behavior so we can infer what we wanted to infer about it, but in reality, other cases, other states with the same kind of treatment wouldn't have this outcome. all that said, and there's lots more besides those, there's many more threats to validity. But our goal in all these cases is to improve internal validity, right? To isolate our causal effect. The goal in all of our cases is to come as close as possible to a true experimental design in which you have a comparison that exists in which only the treatment, only the single independent variable changes between what we call a treatment group and a control group. Right? That's the goal. The goal of all the stuff we do is to get as close as possible to that gold standard. Right? It's to take a large population, split it at random into groups, and manipulate the treatment, the X, the independent variable, in only one of those groups, and to see if there's a change, the difference between the group you manipulated and the original control group. The goal, of course, is to rule out all rival explanations for the change in Y, except for the change in X. The standard experimental design does this, again, via randomness. Right? You randomly divide subjects into two groups, a treatment group and a control group. You don't present the control group with the stimulus, right? They don't get the different value of X. They get the original value of X. You measure the outcome variable Y in each group afterward, and then you assign any difference in the outcome variable Y between the two groups to the cause of the treatment, right? Why? Because the idea is that random assignment makes it very likely that the groups on average are the same in all ways except for the stimulus you applied, except for the treatment, assuming large enough groups. Right? So think about it this way. If you had, say, 10 million people in your study, and you assign 5 million to the control and 5 million to treatment at random, then most of the things you might think about that might have affected the behavior of the treatment are probably the same in the group 1 and group 2, in control and treatment group. Right? So maybe you think so if this was like a medical trial, you might think some underlying condition made people respond differently to medicine. But if I had 5 million people in each group, the proportion of the population in group 1 that had this underlying condition is probably pretty similar to the proportion of group 2 that had this underlying condition, and therefore the effects of the treatment, if we're different in that group, should be the same. That difference should show up in both groups. So that is, in some cases, that was a little fuzzy example, but the idea is all the things that might affect the effect of the treatment should be the same in both groups. So the average behavior of the treatment, not necessarily specific behavior within subgroups, but the average behavior of the treatment should be the same, should be due to the treatment itself and not due to differences between the groups. Okay. There's two elements to that randomness, right? Random selection and random assignment. Random selection is that each case has the same chance of being an experiment, right? So when I'm picking people to be in this population to fill out my control and treatment groups, I'm not selecting certain populations. There's actually a frequent problem in a lot of studies, medical studies, for instance, in which you select individuals who have a particular underlying condition you're trying to fix with the medicine. That selection isn't random. You're selecting all people who have this particular condition, which you do because you want to fix the condition and not give medicine to people who are healthy. But that said, that condition might be due to a bunch of underlying factors that make that subpopulation different from the population as a whole. So selection isn't always random. Ideally, you take the entire population of the Earth and pick people at completely at random and populate your control and treatment groups that way. So you pick, say, 20 million people out of the entire population of the Earth at completely random and put them in your study. And then random assignment is you split that 20 million people up into groups of 10 million equally randomly. So each person has an equal chance at random to be placed into the control or treatment group. So there's no bias based on individual characteristics to be in the experiment in the first place, and there's no bias about which control or treatment group you're placed into. So ideally, the groups you form then are equivalent in all ways other than the treatment you give to one group. Therefore, any difference you observe between the groups is due only to the treatment and not due to other factors that might be present. And that's key, right? It eliminates potentially the threat of a spurious relationship, right? Because it controls for all the possible other things that could matter. Anything we could measure but haven't measured, well, it's the same in both groups. So it wasn't that makes a difference, right? And it controls for observables, right? Even things we didn't measure, it controls for, right? So sure, there might be things we didn't think of that could have mattered, but they're the same in both groups. So if the groups are different, it wasn't due to that thing we forgot to measure because they're the same in both groups. So I couldn't explain the difference, right? In general, things are the same. In a comparison setting, things that are the same in two different groups can't explain differences between groups. So if the only difference between two groups is a treatment, then we can assign the treatment, we can assign causality to the effect of the treatment. And that's the key of experimental design. That's why it's so useful and so helpful and so central to most of the scientific endeavor. Problem is we have a real hard time doing that in a bunch of cases in political science. That's changing in the near term. We're moving to much more experimental designs as we advance in various ways. But in general, there are a lot of things we think matter quite a bit to behavior that can't be randomly assigned, right? Gender, religion, war, these are all things we can't actually just assign to a treatment group a priori. They exist already. Or in the case of war, it would be absurdly unethical to try to assign to a treatment group. So that's one problem, is we can't actually make this random assignment in a lot of cases. Two is that there are differences between the lab setting and an actual world, right? In some cases, the lab is probably pretty similar to the real world, right? If I took, we don't necessarily think that there's a lot of differences if I give people some medicine in a treatment group and do that in a room versus do that in their homes. There might be differences based on diet or sort of mobility and exercise that affect how the medicine works, or sleep. But by and large, we think giving them the medicine where they are, the medicine's probably doing most of the work potentially. But if it's not, there's problems with transitioning between the lab and the actual world. In political science and the social sciences, it's much more stark, right? Asking a person a question about whether or not that person would go to war in some cases may be very different than what a policymaker thinks about while having the actual possibility of going to war. People's psychology may be very different in those two cases. Maybe they're not, in which case you can use the lab very effectively, but maybe they are, and that's sort of an open question in a bunch of dimensions. So that's what we call external validity. Whether or not my experimental design has a wider scope condition or generalizes beyond the actual population in the lab itself. Okay. A third problem is the problem of convenience samples, right? We don't necessarily get the sample we want. We might want 20 million people at random in the entire population. Instead, we end up with 200 college students, right, to run an experiment in the lab. And maybe those college students are different in fundamental ways than the larger population, and if that difference affects the response to the treatment, we're in trouble. All this says, this doesn't mean you can't run experiments in social sciences. I'm actually teaching a new class in experimental political science in the fall semester of 2020 the first time. It's a big, broad field and big, broad methodology. You have to be careful. You have to make sure that the ways in which maybe your sample isn't quite representative of the larger population doesn't affect the effect of the treatment, doesn't alter the effect of the treatment, right? So for instance, if I have some medicine I'm trying to test on a treatment group, right, and the treatment group everyone has brown hair or black hair, and everyone in the control group has blonde hair, and I don't think hair color has anything to do with the medicine's behavior, it probably doesn't matter if there's a difference in hair color between treatment and control group. That said, if there's a physical difference between treatment and control group that affected how medicines act differently, then it would matter quite a bit. And you could assume that your treatment effect generalizes to lots of other circumstances, because now the treatment is acting differently because of the differences in the physical behavior. So it doesn't generalize as well. This has been a frequent problem in the medical sciences in terms of gender, because primarily the lab tests had been on men, and they assumed that the effects of the medicines, of the treatments, were just uniform across genders, and they were not. So it's very important to make sure you keep track of the scope conditions of your experiment in addition to your theory, and identify whether or not your sample characteristics are not unique in some way that affects the effect of the treatment. You want them to be unrelated. Differences between your sample and the larger population you care about should ideally be unrelated to the effect of the treatment as much as possible. Okay, so let's go back to the Connecticut one. That was not in any way, shape, or form an experimental design. They didn't randomly assign a treatment. They assigned it for some reason, right? Maybe the high fatalities right beforehand led them to change the rules. So how could we design an experiment to test the effect of speeding and fatalities? Well, we might choose two regions that seem very similar, right? And then institute, say, a reduction in the speed limit in one case and not the other case, and then observe differences. And hope there's nothing else different between those two places that led to the differences you observed post-treatment. This might have ethical problems, right? If you know, for instance, that reducing the speed limit reduces fatalities, and it does, usually, then is it ethical not to do it in one case? Medical researchers often have this problem in terms of experiments. When they start discovering that, in fact, the medicine works really well, there's an ethical issue in continuing not to give it to the control group. So this can be fraught. And there are university institution review boards designed to assess the ethical nature of your experiments. Although not as much as they potentially should focus on. They also assess other things as well. But they also consider the ethical nature of your experiments. Okay, when you can't do a lab experiment, there are various quasi-experimental designs that political scientists and economics and sociologists make use of to try to make progress in this way. One is called a field experiment. In a field experiment, you basically take a lab experiment but do it somewhere else in the real world. So instead of doing it, in the lab, which might be like in a university with college students, you go outside the lab to a rural location. The university isn't a real world, but to a location outside in the world in the area you care about the population of, and you perform the experiment there. That's often called lab in the field. A field experiment is a little more broad than that, which is that you can do any kind of treatment there. So for instance, if you want to test out a policy, you can choose two different regions that you think are very similar and apply the policy to one region, not the other one, and assess how the regions differ after the policy is enacted. That's a field experiment. A lab in the field is more you just do the lab experiment in the field. Lab in the field experiments are designed to just get around some of the external validity problems of having a non-representative sample. So having a sample population that's not representative of the larger population. The field experiments are designed to get around that even more by directly looking at the policy's effect that you care about. Right? Looking at the policies you care about and their effects and how the policy changes different things. In general, the further you go away from the lab type randomization, the more you lose in internal validity, but you might gain a whole lot in external validity. So it can be a trade-off. Natural experiment is a quasi-experimental design in which something happens outside your control, hopefully at random, and then hopefully unrelated to any treatments that you care about, and that separates people into a treatment and control group. So I'll conclude with a couple examples of each one of these. Okay, so the field experiment example might be an experiment on turnout. There are a lot of these. The idea is we want people to participate more in the electoral process, get out the vote drives, right? We want people to come out to vote. What's the best way to get them to do that? So you might run an experiment in which some people in one treatment group, received door-to-door canvassing of individuals knocking on the doors and talking to them directly. And a second group might receive telephone calls, exhorting them to come out and vote. And a third group might receive mail, direct physical mail or email designed to get them to vote. And then you might compare the three of those different cases to see, and then a fourth group might receive nothing. You might compare all different cases to see what the relative effects of each of these treatments are. The good part about that is it's random assignment of the treatment, right? You randomly assign who gets the door-to-door canvassing and so on. However, because people's homes are not randomly distributed across neighborhoods, the assignment isn't truly random, right? There might be differences across neighborhoods that might make it harder to actually claim you have pure randomness. For natural experiment, these are both things that actually happened in the literature. This one, you might have you care about the effect of newspapers on political information, and then in one case you have a strike. So in this case, it happened to be a strike. It was Pittsburgh and I think Cleveland or in Ohio. I think it was Cleveland, definitely Ohio. So you had a strike in one place, not the other place, and the argument was they're pretty similar, which I know people in either place don't like. But the argument was they're pretty similar otherwise, except for the strike that happened for unrelated reasons in Pittsburgh. And you can try to assess then what the effect on individuals, political information level was post-strike, to see if there's a difference in the information individuals had in Ohio versus in Pittsburgh. Again, there's random assignment of the treatment in this case. You can assume because the strike didn't happen for a particular reason related to information acquisition, but the people's homes between the two different states are not the same. The states themselves might not be identical in all the ways that are important. So it's not truly random. And note, all these kind of quasi-experiments exist because we're assuming that everything else is the same. So when I go door to door versus give email or give a phone call, I'm assuming that those people I'm talking to in either case are the same besides the treatment they got. Right? In this case, for the natural experiment, I'm assuming that the two different locations are the same and people respond the same to political information and news in both places, except for the lack of access to newspapers in one case. Right? If you don't believe these claims, then you don't believe the experiments are valid, they don't have internal validity, and that is fine. You're allowed not to believe that. But that's the underlying logic behind these. And in general, we exist in a continuum between sort of pure lab experiments that have total randomness in large populations, which are kind of rare in political science. And as we go to the other direction, we go to these quasi-experiments in which we don't randomize everything, but we try to randomize as much as possible. We won't talk very much about experimental designs or experiments from now on, just because primarily what we're dealing with in our experience are observational data in which we can't control all the various differences between groups, with the exception of using statistics. So we'll start now discussing research designs that are non-experimental.